Yeah, thanks so much, and thanks so much for having me. I will talk about the why and the how of taking open source ROS to a safety certified robotic software framework. And at the end, also a bit about our experience, what worked, what didn't, the challenges we encountered. A little bit of history first. As pointed out, I started my PhD work in Braunschweig in autonomous driving. In the late 90s, built up a completely driverless vehicle. Today, we would call it a level 4 vehicle. One of the challenges we faced back then, cars didn't have any actuators, any electronic interfaces to actuate the vehicle with. So we first had to build this robot to sit on the driver's seat based on a robot for emission tests. So a robot with 3 legs, with 3 pedals, an actuator for the steering wheel. Later on, we added more actuators for the levers behind the steering wheel. Actually worked beautifully. But the end, the robot alone was more expensive than what the customer wanted to pay for the whole system. In addition, we had to work with very early stage LiDAR. So the blue boxes on the front were LiDARs we took from industrial automation, camera, pre-production radar. So really everything was pre-production. That started 2 years before the first driver assistance systems hit cars as a product. Then I spent a couple of years prototyping what we at the time called advanced driver assistance. So on the left, you see, we call it traffic jam assist. It's essentially a level 2 system, very similar to what Autopilot has today. And on the right, we prototyped a left turn assist, prevents you from making unintended left turns into oncoming traffic. Prototype here was done around 2004, 2005, and then it took another 12 years to make it into a product. And that already tells you a bit about the speed of adoption of innovation in the automotive industry. Late 2006, I moved here to Stanford. I'm here in the bottom right of the picture to work in Sebastian's lab for a couple of years during the DARPA Urban Challenge. Since 2010, I teach MB3 at 2B. And then around 2009, I got involved with Willow Garage. Willow Garage, a company here in Menlo Park, started by Scott Hassan, one of the earliest Google employees, who wanted to make progress in robotics. And then he found it's very interdisciplinary. There's not a lot of collaboration going on between software, hardware, electronics, and so on. So he then took a project here from Stanford. Ken is here, great to see you again. The PR1, and they rebuilt it to make the PR2. PR2 was then a very capable, I believe, 27 degree of freedom robot, which could get you a drink, could play pool. And then another project was taken here from Stanford, which was Switchyard at the time, which Morgan wrote, I believe, in Andrew Ng's lab. And that then became ROS, the robot operating system, which was really the first capable, omnipresent, widely spread robotic software framework. Then Willow Garage built 20 of these robots, gave 11 away for free, and for free under the condition that everything the recipients would do with it had to go back into ROS, and that's really how ROS got jump-started. 10 went to universities, including Stanford here, and 1 went to a corporate lab, and that was my lab at Bosch. I'm right on the gray shirt here in this image. Now, fast forward 12 years, ROS is really omnipresent, not just in academia, but also in the industry, widely adopted for prototyping. You can see pretty much every major automotive player uses it. But then ultimately we found everybody gets stuck taking the prototypes, which is greatly accelerated into a product. I was then at Bosch at the time. We were the first company to support ROS. Then did a lot of robotics projects with it, teaching robots how to cook, teaching robots how to deliver mail, use power tools, fold T-shirts. Then we started to use it for product development. We used it heavily for the development of software for the robotic lawnmower. Ended up not being able to fit it onto the embedded system. ROS1 was simply too heavy, and the embedded microcontroller was simply too small. Then we spun it out. We spun out a company called Mayfield Robotics to develop consumer robots. That company then shut down a couple of years later, pretty much as all the robotics toy companies in the space. Then we took ROS into agriculture, and then we also took ROS into autonomous driving. and rewrote the Stanford software we used during the DARPA Urban Challenge to run on ROS, and that was the first vehicle which ran that software, and then we built up another one, built based on a Tesla platform. Then I left Bosch, joined a car maker, Faraday Future. We again used ROS for prototyping. We again got stuck taking ROS into product. And that then led to the idea of starting a company. Started Apex.ai a little over 5 years ago. And in a nutshell, what we do is we have taken ROS 2 actually at the time, which came out end of 2017, early 2018. And we more or less rewrote it from scratch based on the same architecture, and then spent about a year certifying it to the highest level of automotive functional safety. And that's that process I will talk about today. Just very brief background on the company. We are venture funded, obviously. Here, various Sand Hill Road investors, Lightspeed Canaan invested. And then fairly early on, the automotive industry became interested, and we have by now 10 strategic investors, as you can see here, car makers and tier ones, and also agricultural companies. Company is now over 100 people. We are present in 8 countries with 5 offices and 4 entities. And that now brings me to the topic, how we took open source into an automotive product. When starting the company, we looked back roughly on 20 years of robotic software development. And what I noticed is the first 10 years of my career, there was no reuse. Basically, for every project, we rewrote everything from scratch. As you can see, project lasted at least 3-4 years. All of a sudden, ROS came out, and we were able to prototype applications in a couple of days to a couple of weeks. So the process of prototyping was greatly accelerated, and that really taught me the power of a software platform. And what we are now doing is taking that from a prototyping platform into a product platform. Another way of looking at it, the first 10 years of my career, basically we redeveloped every idea 3 times. For proof of concept, a prototype, and then a product. Each of those steps in automotive takes at least 3 years, sometimes 4, and then you end up with innovation cycles from ideas to product of way beyond 12 years. For simple functionalities at the time. And then it's really not a surprise that developing a robotaxi or a much more complex application in a highly safety regulated domain like automotive takes more than a couple of years. With ROS, really the first stage of that process was accelerated with ROS 2, which came out, again, end of 2017, early 2018. Also the prototyping stage, because it's closer to real time, more reliable, got accelerated, but still taking it into product. More or less all companies deviated from ROS and either did their own thing or rewrote it. And what we have now developed is one system that you can take from POC over prototype to product. In that regard, the automotive industry today is really where the smartphone, the IT industry was about 15 years ago. 20 years ago, I had one of these Nokia phones, then just had arrived here at Stanford 2007. The first iPhone came out. And that's exactly where the automotive industry is today. Taking cars from a hardware-centric device to a software-defined device, where you can add functionality also during the lifetime, and add software and add functionality by adding software. If you buy a car today, functionality over the lifetime typically does not change. Yes, maybe you can download a more up-to-date map, but that's pretty much it today. And really the enabling factor was not the device, it wasn't the app store, it was the software development kit, which sits in between the base software of the device and the application, and it abstracts all the embedded hardware on the device, which really isn't that much different from the embedded hardware on a car today, and makes it so simple that every student, also a high school or middle school student, can essentially develop complex software for a complex embedded device. So what we are focusing on is ultimately enabling deterministic real-time performance on a very resource-constrained embedded system, such that large software development teams can work efficiently and be productive. And by large, the software development teams at a car maker or a tier one, they range everywhere from a couple of dozen people to a couple of hundred or a couple of thousand people. And most of them are not experts for programming embedded systems. They're experts for perception, planning, and really expert on the application level, but not experts on the embedded programming, real-time, creating deterministic software level. So we then looked at, to understand what we needed to do in order to make ROS or ROS2 a capable proprietary real-time deterministic software package. We found a couple of things. We needed to change the memory allocation, threading, remove all the blocking calls. So for instance, in ROS2, you read in sensor data from a LiDAR from a camera. ROS2 allocates memory on subscription of a topic, on subscription of a memory. That's highly dynamic. It's great for prototyping because it enables you to prototype quickly, but it prevents you from creating ultimately a deterministic real-time system. So what we ended up doing is we ended up rewriting all the memory operations in ROS and the underlying libraries. That pertains to all the standard library containers, which you typically use, so the whole STL library. But then also we noticed we needed to deal with exceptions. I'll come to that in a bit. Then the whole data transport, so getting data from one process to another process, or in case of a car, you have anywhere between a couple of dozen and a couple of hundred so-called ECUs, so computers spread around the vehicle. So you need to get data from, let's say, the radar sensor to the computer processing the radar data. So that's the whole data transport. And then we tackled the whole topic of threading, where in ROS and in any research software, really, you can't control sufficiently threading priority, scheduling, CPU pinning, so assigning tasks to a certain core, for instance. You use blocking calls. Blocking calls are writing to disk or writing to the network interface. If your disk is full, you don't want your car on the highway to all of a sudden stop reacting. So can't work with blocking calls, can't work with deadlocks. And as I said, an embedded computer on a car is very resource constrained. You want to run very complex algorithms on it. So you need to ultimately make the application as efficient as possible, and such that, a non-embedded software developer can actually do that reliably. So we ended up removing all the dynamic memory allocation from ROS and the underlying libraries. That also entailed writing our own containers, also such that they run on x86 and ARM architectures, such that the application on top doesn't need to change when you move from one architecture to another. We ended up not changing or finding a solution for working with exceptions, but we made the process of catching exceptions deterministic, and that ended up being sufficient. We completely rewrote the data transport for automotive. That I will come to that in the second half of the talk. And we ended up writing our own threading libraries and put a large emphasis on execution management, such that the application developer, so again, someone who develops perception software or planning software, does not need to deal with dealing with multi-threading, for instance, on different target platforms. So we rewrote our own memory allocators, we rewrote our own threading libraries, and I wanted to give you a couple of examples how that then pertains to somebody working on perception over somebody working on planning. So what is an executor? An executor is a piece of software that sits in between the task. So the task could be, again, reading and sensor data and working on, for instance, fusing camera and LiDAR data, and then configures the thread. So how threads run on a multi-threaded system. In ROS-1, which is the original version of ROS, that is essentially a piece of software that takes events. So events could be your camera sends you a camera image, or your LiDAR sensor sends you a new LiDAR frame, and then starts a thread. So a thread then contains whatever you want to process, the algorithm you wrote. That is simple and works well for something simple like a user interface, where you press a button, and then upon pressing the button, you want to execute a certain function, like read the news or turn on the radio. But a typical robotics use case is, for instance, data fusion. Taking data from camera, so a camera image, and taking data from a radar, so radar frame, and then fusing it. So one way to do it is you wait for you trigger on a radar message, for instance, and then you read in the most recent camera image and some transformation that transforms, for instance, the coordinate system of your camera to the one of the radar, or the other way around. But then you have to deal with different cycle times of the radar, different cycle times of the camera, and that ultimately generates a lot of overhead. And so why should the application developer deal with callbacks for messages that you don't need? For instance, here you have a camera image that you're not using because you're waiting for the radar to trigger the processing. Why should you deal with, as an application developer, caching messages until you have one that you actually want to use? So that should all be abstracted from the application developer. So really, the way you want to do it is you want to have a certain triggering topic. So in this very simple example, that would be a radar message, and then the system, in this case, the executor, provides you whatever you need in terms of data. So the most recent radar message and the most recent camera image, for instance. But then you have other use cases like planner execution. So you don't want to run upon getting the latest radar message, but you want to run exactly every 10 or 100 milliseconds. So then you need an executor that can be triggered by time. So that is the example here. But then in order to make that robust, maybe you need both. Here, the use case here would be you really trigger on radar, but let's say the radar is down. You don't want to wait forever until you execute sensor data processing. So you would then trigger on radar, but in addition have a timeout. So let's say 10 or 100 milliseconds. So you do some processing in the failure case where you haven't received a radar message in a certain amount of time. But again, imagine an engineering team of a couple of hundred or a couple of thousand people. You don't want every sub-team to come up with their own solution for this. So really that needs to be abstracted by the software framework. And then there are more use cases like multiple execution conditions, or you don't want to execute just a single item, but have a directed graph of items that could be linear, or could also be several execution items in parallel. That is all possible, and that is actually with an executor like this, and the simple version now exists in ROS2. We contribute to that in open source, and then the real-time certified version that exists in our software. So that is one example of the additions we made to ROS2. Another big one is vehicle communication. So by vehicle communication, I mentioned that earlier, you have anywhere from a couple of dozen to a couple of hundred ECUs. essentially embedded computers around the vehicle, and they're typically separated into domains. So one domain would be the body, that's the air conditioning or the windows, so everything that is entailed in the chassis. Then you have the powertrain, that is what drives the vehicle. ADAS is driver assistance. Infotainment is the radio and the telematics unit and the for instance, the screens. And then telematics is essentially a cell phone modem, a firewall, and a switch that connects the vehicle to the cloud. All these different domains typically use different protocols. In addition, the amount of data to be processed has grown tremendously over the last 10, 20 years. In a 20-year-old car, basically a couple of messages in the kilobyte range being sent around so that the engine can talk to the cluster instrument and the braking system, for instance. Then driver assistance came about 10, 15 years ago. Cameras were added, and now you have vehicles with up to a dozen cameras, with anywhere from around 25 frames per second in the megapixel range on a vehicle, and that then quickly gets you to gigabytes of data per second. So they have to now be piped through the processing pipelines. In addition, vehicles today are connected. They're connected to the cloud, they're connected to infrastructure, such as traffic lights. There are systems that warn you of pedestrians crossing the street, for instance. So that then adds a number of other protocols. Also, software architecture of the vehicle is changing. So pieces of software get moved around in the vehicle from one, for instance, from one ECU to another. And that really shouldn't have to change the application software. So what we ended up doing is writing a piece of software also based on open source that can deal with all those different use cases, but application facing provides one API. So the application developer shouldn't really deal with what the underlying bus and the underlying protocol is. In practice, that looks something like this. So the by now predominant bus in a car is Ethernet. It's actually Automotive Ethernet, but de facto Ethernet. But then there are also some of the microcontroller-based ECUs typically connected via CAN bus, which is a very simple automotive bus. And then you have also more complex computers here, for instance, an automated driving domain controller, which consists of one or several SoCs connected by an Ethernet switch, and then also microcontroller units here. Then the protocols that either run on Ethernet or then run on CAN is on CAN, obviously CAN, but on Ethernet that can be some IP, which is an automotive protocol, or DDS, which is a more modern robotics protocol, which ROS2 also uses. But then there are also cloud protocols like MQTT, or if you want to watch a movie in the car, you need some video streaming protocols. But again, ultimately the application, and that now goes back to ROS2, to the application, it shouldn't really matter which underlying bus is being used. So application-wise, ROS uses so-called topics. Topics are essentially a data channel, and then you can publish and subscribe data to that channel. And one or several subscribers can receive data, and one or several publishers can send data. Actually fairly simple. In ROS2 and most applications with complex processing, you have a number of different processes. Let's see here, you have a LiDAR. The LiDAR sends data. You read in the data. You transform it to some other coordinate system. You fuse it. You filter ground. You detect clusters, so objects, and then you do a collision estimation. Using ROS2, so just for sending the data from one process to another one, that roughly takes 5 milliseconds for a substantial amount of data. The reason is it uses a network stack. And the network stack then requires to serialize the data. It entails copies. The larger the data grows, so in case of camera images, that results in a lot of copies and a lot of data being copied, and then you end up just for the messaging pipeline of latency somewhere around 25 milliseconds. If you now take into account that a car moves with several meters per second, that is actually a lot of time. So the car will have moved just through during the time which it takes to copy, to serialize, deserialize, and copy all the data. So newer technology, what we have then also added to ROS2 is a so-called shared memory data transport, which is actually quite logical, but not the normal way ROS or any other messaging robotic software does it. So you write data into a pre-allocated memory pool. You put it in once, and then the subscribers take it out of the memory pool just by passing pointers around and not by copying the data anymore. And that then is obviously, because you're just passing pointers with a fixed size, is size agnostic. So you stay in the low microsecond range, completely independent of the message size. Whereas we here ran that on the real-time system for working with camera, image size data, you quickly get into, again, the high millisecond latency amount. So that makes obviously a huge difference. And that then brings me to the last topic, which is safety certification. Automotive and other domains in which operation can lead to damage or injuries or death are highly safety regulated. In the automotive case, that is governed by a norm called ISO 26262. For machinery, it's typically IEC 61508. So there are a number of norms that pertain both to system safety and then to software safety. And ultimately what they are is a collection of safety goals. So depending on the criticality and the possible effect of a safety critical failure, you do so-called safety analysis and hazard and risk analysis, and then you come up with a certain safety rating. In automotive, that ranges from QM, quality managed, meaning you just put in some quality measures, to several levels of so-called safety levels, and they are A, B, C, and D, D being the strictest. And the requirements for system safety on the system level are roughly such that for the highest level, ASIL-D, the system prescribes there shouldn't be more than 10 potentially safety critical failures per 10 to the 9th hours of operation. So very few failures in a very, very large amount of time. Also such that you cannot show statistically anymore that you've met the safety goal. So the way to then meet the safety goal is really by applying all the safety best practices that the norm recommends. And then in Europe, you actually have a third-party company, an assessor come in, and they then audit you and both the company and the product, whether you've met that. Again, for automotive, that's ISO 26262. And in this case, a software package is like ROS, in our case, safety certified ROS, has really been developed independent from and actually before the final application. So when ROS was developed, ROS developers didn't know how it would be used later on. When we certified, we didn't know, and we still don't, how future customers may be using it. So the norm calls that a safety element out of context. So a safety relevant element which was developed outside of the context of the final application. And there's a specific process for this. In a nutshell, what we did is we first looked at every ROS package that we wanted to certify, and we reduced the feature set. So obviously we don't want to certify stuff that is in the end not needed. Then we worked through all the processes that I mentioned earlier, so elimination of runtime memory allocations and blocking calls, for instance. Then we applied a static coding analysis, and you can both use open source tools or buy proprietary tools. So this is up to here, it's really all standard. Then came the labor-intensive part. So that's tests, tests, and tests. So for reaching ASIL D, the highest level, you need to have really 100% test coverage for all statements, all branches, and a MCDC, which is modified condition decision coverage. So you need to make sure and show that for all possible conditions in your software, for instance, in a nested if statement, you're really running through all the conditions, and you've tested all the conditions. That is for complex software actually not trivial. Then you need to write requirements. What that means is really all the code you're writing needs to have a purpose. The purpose needs to be clearly defined and described and tested. And then you need to generate and show full traceability from each requirement to which code does the requirement, which requirement is fulfilled by which part of the code, which code fulfills which requirement, so bidirectional traceability, and the same for tests. You need to show which tests tests which part of the code and fulfills which requirement. Then there are a number of specialized tests. Then you need to do a so-called failure mode analysis. Then for all the tools you're used, you either need to have a so-called tool classification, or you need to generate one. For instance, for the coding tests, the coding guidelines, the MCDC tools, and so on and so on. If you're using Excel to manage your requirements, you need to qualify Excel, to use Excel for safety critical application, and so on and so on. Then you need to look at a lot of architectural metrics, such as the cyclomatic complexity, which is really a measure for how complex is the software that you've written. Then you need to document everything, including architectural diagrams, do control and data flow analysis. Then you need to test on all target platforms. So a target platform is ultimately the device the customer, for instance, a car company, runs the software on. So that could be an NVIDIA board, a Qualcomm board, a TI board, and in our case then also the combination of the actual kernel, so the real-time operating system on top. And that then quickly leads to a fairly large number of possible hardware platforms we are testing on. And then you need to generate so-called safety artifacts. Safety artifacts are really the safety plan, a safety manual. So that contains all the assumptions we've made and all the conditions under which we've tested. And that's specific then also to a safety element out of context. So let's say a customer comes in 2 years and uses the software on a computer which we haven't used during testing when we did the certification. Then that's a violation of the safety manual, and then we have to add those tests later on before the customer can obtain safety certification for the final product. But the purpose of safety certification as a safety element out of context is really that you can save the additional certification step later on. But if you as students later on ever want to take a piece of software and sell it into safety critical application, roughly these are the steps that you have to walk through. So for ROS, to give you some estimate on some effort estimation. So steps 1, 2, and 3 for ROS2 took us roughly 2 years with a team of, at the time, 30, 40 persons. And then working from 4 to 13 was roughly another year with a team by then 40 plus persons. So roughly 40 person years and maybe 100 person years, 50 to 100. And then at the end, we got a certificate, so really a one piece of paper, which shows safety certification achieved. And then obviously software is never finished, so there are new software versions. We would then, which we haven't done since, but we will eventually, then you need to do so-called delta certification. So you need to look at the difference, what has changed, and then possibly recertify with your certification partner. That then led to our first safety certified version of ROS, which we then started to roll out into automotive. And I'm not going to spend the next 10-ish minutes to talk a bit about our experience doing that. So first, a bit of a background. So what does an architecture in automotive look like? Going back 20 years, the blocks here are either sensors or ECUs, so computers. It was really very simple. Whatever needed to be connected, somehow was connected. Mostly the ECUs were running independently, and there was very little networking going on. So those are the cars roughly 20 years old. Then the number of ECUs started to grow from maybe a dozen to a couple of dozens. And then the first compartmentalization into so-called domains started. So all the, let's say, AC computers, window lifters, computers, ECUs that control the lights were grouped into so-called body domain. Then you have the chassis that pertains to suspension and braking, powertrain, and so on. And then you typically had more or less three to four more or less independent networks in a car, which were loosely connected whenever it was needed. So let's say your infotainment domain, which drives the cluster, which is really the instrument, needs to be connected to the powertrain because the powertrain shows you the RPMs of the engine, and it needs to be connected to the chassis because there are wheel speed sensors which measure how fast the vehicle goes. But really loose on-demand connection. Then more recently, so roughly around 5 years ago, the so-called central gateway was added. The central gateway is really a cell phone modem, a firewall, and a switch, which then connects the car to the internet. For instance, to get you the latest map for the navigation system, or do some simple software updates. Industry is currently in between the third and the fourth generation of vehicle architectures, and then the fourth generation adds so-called domain controllers or domain computers. These are now for the first time more powerful microprocessor, multi-core computers. So actually very similar to what is in my iPhone, for instance. Whereas all these here are really single-core microcontroller-driven, fairly simple devices. The reason is, for the introduction here, current and future vehicle functions require more compute power. So that is for the infotainment system rendering content on multiple screens, to driver assistance systems or automated driving performing more complex functionality. Tesla has domain controllers in their vehicles for a couple of years already. Most other car makers are in the process of introducing that architecture in the next couple of years. Possibly there will be a fifth generation, which then really where the idea is you have one central computer in the vehicle and all the devices that are connected to it then run only very little software, typically just a bus and a network interface. And then here you have really one server-grade powerful computer with a compartmentalization of domains done virtually, for instance, through virtual machines and hypervisors. But the issue now that arose is the automotive industry, being automotive industry, introduced a new hardware architecture without really having a software architecture that can support the hardware architecture. McKinsey, this is a graph I borrowed from McKinsey, roughly shows it like this, normalized here to 2008, so 15 years ago. McKinsey thinks that between then and now, the complexity of software has roughly increased by a factor of 3. I would argue it's actually significantly more. And they also show that the productivity in the automotive industry has increased only a little, whereas here the productivity of the tech leaders, referring to Google, Apple, Facebook, has increased, but by far not as much as the complexity of software has increased. That's the message of the slide here. The bad news is McKinsey thinks that gap will get even larger, roughly by a factor of 3 from today to 2030. I think it's going to be significantly more. And the practical result are actually software bugs, and in case of the car industry, delays of production anywhere between, also of rolling out a car that is produced in hardware, where the software either isn't working properly or they can't get it to work in the first place, by months to years. And we've had several car makers experiencing that in the past few years. And sometimes it also makes it into the news. For instance, the New York Times, the Wall Street Journal had a big article around software delays and the billion-dollar damage it caused just a couple of months ago. Another interesting aspect of this slide here is this factor 2 between the automotive software development productivity and the tech leader software development productivity. So why is there a factor of 2? In automotive and in robotics, we are in a safety relevant domain, so safety is just harder. As I pointed that out earlier there. 9 of the 13 steps really pertain to safety. Security is harder. You don't want your car or robot to be hacked. The automotive industry is really suffering by this hardware-first approach. So the automotive industry is historically a hardware industry, and not a software industry. So I pointed that out in the architectural slide. Automotive industry introduces a hardware architecture, and then they notice, hey, the software architecture, the software to support it is missing. It's also hard for the automotive industry to get software architects, so the one that really drive new software, because Google, Apple, and Facebook suck them all up. And it's not as sexy, not as appealing working on a car where the innovation cycles are many, many years versus a consumer device where you can see your work in a product in the next few weeks or months. So that's just how it is. In addition, there are actually in C++ 17, C++ 20, or Rust, for instance, new languages and new language features that help to abstract complexity in software to a great extent, but they are hard to use for safety-critical applications. So a substantial amount of our time went into reducing the feature set that we use and then we allow our customers to use of C++ to the functions that we deemed appropriate for using in a safety-critical applications. So there are a lot of functionality that reduce the software complexity, but you can't really make them being used in a safe way. And then for the automotive industry, making investments is just hard. In a good year, car companies have a profit margin of a couple of %, whereas in a good year, an internet company has a 10 times higher profit margin. So that's it's just hard to make investments. But nevertheless, all of the complaining doesn't help. Productivity needs to go up. Then we started to roll out the software to our customers. And we expected to encounter something like this. So 4 or 5 domains, body, powertrain, ADAS. You then have the respective controller. So let's take ADAS, an ADAS ECU, so a multi-core ARM-based computer with a base operating system, so an RTOS that could, for instance, be QNX. A middleware, so the data transport, some software platform, some APIs, maybe a couple of suppliers that then deliver the application software, let's say for parking aids or for adaptive cruise control. And then you have the functional software. In reality, we encountered something like this. A wild mix of suppliers, inconsistent APIs, running on one ECU, several implementations, for instance, of data transport software that more or less does the same, but really driven by one or several suppliers here on top. They then use all their stuff. Then the next supplier has the same functionality implemented differently. Then the OEM, so the manufacturer of the car, wants to add some functionality. These are actually not available as source code to the OEM typically, because the supplier keeps them proprietary. And then they do their own implementation on top. So more than once we encountered a situation where software for the same purpose was running several times and being implemented and then needs to be cemented several times on one ECU. So highly, highly inefficient. And that then also leads to the productivity gap. And it leads to resource issues on the device. So we've encountered several times situations where a substantial amount of the computing resources were eaten up by the base software, not leaving enough resources for the functional software. The solution would actually be simple, having one operating system across the whole device, one data transport software, the so-called middleware, one software framework, one application API, and then all the functionalities on top use that same API. Reality is different, and the reason is there's just a lot of legacy software in automotive. In a car is a very complex device, and from one generation to the next, there's a lot of reuse. And you can't redevelop realistically software and functionality for whole car for each generation from scratch and completely based on new APIs. That's just how it works. Another way to look at it is a so-called V-cycle. The V-cycle is really a model that shows how cars or complex mechatronical devices are developed. You basically start with requirements describing what should the device do. Then you break them down first into systems. So a system could be the braking system, the powertrain, the steering system, and so on. Then you break it down even further. Here, then the separation into mechanical systems, electrical systems, software systems starts. At some point, you reach the component level. Then and only then you start with the actual implementation. Once it's implemented, you run up the right half of the V again, and then on every layer you check whether what you've implemented actually matches what your requirements were. At some point, you put everything together, and if you do that in software, and that's really up here, the system integration and the vehicle integration, when you do that in software, based on non-identical APIs, so every domain using their own APIs and framework, you don't run through the V-cycle once, but you run through the V-cycle dozens or 100 times in parallel. And the resulting issue is you notice issues very late. Let's say very simple case. The message one, super simple case. The message one sensor sends doesn't match to what an ECU expects. So you need to change a message parameter. Could actually be very simple. But since the OEM doesn't have all the source code, only the suppliers do in a car today, you need to go back to the requirements, see what went wrong. You need to run through the whole V cycle again. And that sometimes takes a couple of months. And that then leads to a couple of months for a simple software update to do one simple fix. And that then contributes to the lack of innovation speed in the automotive industry today. If a software-driven company would have all the software and source code and can do a new software build overnight. But that's not where car industry is today, at least not the traditional car makers. But ultimately, where the automotive industry needs to get to is one software layer, one SDK for the whole car. And most of the car makers have actually realized that. Some are getting that software from us. A lot are doing it in-house. But it's slowly but steadily settling in that car makers need to move from being hardware-centric companies to software-centric companies. That brings me to the end. We've rolled it out in the meantime to our software to many domains, not just cars, robotaxis, trucking companies, marine boating companies, so really any robotic mechatronical system that where you can use ROS for prototyping. We in the meantime have done projects in. With that, I think we have about 8 minutes for questions. I'd be happy to take any questions you like.
Have you looked at fulfillment centers like Amazon, Walgreens, and Walmart, rather?
We haven't. So a lot of the fulfillment centers actually, so not Amazon, for instance, but a lot of the robotics applications run ROS. Their way to achieving safety is often different than in a car. So those robots often run ROS unmodified, really not being safe and not being safety certified, but they do achieve system safety by running a so-called supervisor, which then often uses an independent sensor, often a LiDAR, and an independent safety-rated computer to then simply detect, has the main system missed something? Let's say an object all of a sudden pops up in front of the robot, and then the whole robot is simply being shut down. So very similar to industrial robotics, where you either have where the robot is gated off or fenced off, or in the more modern system you have a virtual fence based on a LiDAR, for instance, where then everything enters the safety zone around the robot is simply shut down. So that's typically how slower moving robots in fulfillment centers realize safety.
So thank you for your presentation. My question's about, I was struck by the latency of some of the legacy protocols, specifically the passing the information between their different processes, like the Ethernet, specifically the car Ethernet protocol. Mm-hmm. So I guess the question I have is, is prior to actually implementing a new type of software architecture, did it not occur to anyone to actually upgrade, to move away from a TCP/IP stack to something like a shared bus, shared memory, like you're actually using today? Or it seems like, because TCP/IP, it's great, but everyone's known for a long time. It's just you stack on a lot of layers and you have to take all of them off in order to get back to the data packet. Mm-hmm. And of course, there's all this overhead back and forth and errors and memory. So anyway, there's a lot of stuff in TCP/IP, Ethernet. So It's just kind of like it wasn't an era, or like car manufacturers never had to contend with that before now because we didn't have all this data, all this information fusion prior to now. And so yeah, I was just curious about. I mean, it's so anyway. Good innovation that it's doing shared memory and pointers much more efficient, much faster. I'm
And
just
it's
curious.
not rocket science, it's really common sense. Right?
Yeah, exactly. And it's just curious, like there was no evolution between Ethernet to then to.
Yeah, so the reason is really lies in the traditionally hardware-centric approach and mindset of the industry. So as I pointed out here, historically, you really had one box per function with a single core and a single thread running on a microcontroller. So one box with a radar, I could have actually brought one today, where then the whole functionality was implemented on the microcontroller and the radar. And only more recently, namely pretty much where we are today, functionality is now moving from this distributed system into a system where you have larger multi-core computers, all of a sudden parallel processing and multi-threading. And yes, up to now, the software to support that has been missing. For those of you who are using ROS, I should have mentioned the Zero software copy is also available as open source in ROS in a project running under the Eclipse Foundation called Eclipse ISORIX, in case anybody wants to try it out. Yeah.
Yeah, I'm going to ask some of the questions from the students on Zoom.
Sure.
Has a question with regard to the central data storage to decrease latency. With the increasing size of the data transfer to tens of gigabytes per second, do you have to worry about the actual distance between the sensor and the main computer on the robot? Also, do you need to work with a manufacturer to set up multiple data lanes for redundancy?
To the first point, to my knowledge, no, distance is not an issue. The typical car is fairly short. So that is not an issue. The second one pertained, I believe, to redundancy. So it's actually a common misconception that you do need redundancy per se. So what the norm really prescribes as a best practice to achieve safety is the safety level you need to reach. And then you typically do a so-called system decomposition. You break a system down into all the parts. And then if all your components or the failure cases of your components alone cannot achieve the safety goal that is required, then you start to work with redundancy. So for instance, a radar has certain failure cases, the camera has certain failure cases that are known, and sometimes they're unknown. Then you try to combine both such that you have redundancy that both do not show the same failure case. So in other words, do not fail at the same time. But redundancy is really a tool to get to the safety level and not a requirement. There's one over here.
So my question is in relation to the state of software not being continuously updated through generations of cars and in relation to Tesla and what they're doing today. And I'm wondering, what's your thought on Tesla's situation with them being at a disadvantage of developing their own software and what that leads to their development time compared to other vehicle manufacturers?
Yeah. So I showed the V-cycle earlier. A conventional car maker, from the idea and starting with the requirements of what a new car should look like. Let me just show you here. Needs roughly from the requirements level to the final integration, testing, and then producing a vehicle and rolling it out, needs somewhere around 5 to 6 years. Tesla does it in 2.5. Does that answer your question?
Yes. I guess then my follow-up to that would be, why isn't the industry adopting like a uniform platform to start on and then build from that?
If the car industry, if you'd invent a car today, then you would, that's exactly how you would do it. You would start with a platform approach and probably develop one cross-industry standard. And then it's Android. 15 years ago, there was Windows Mobile, BlackBerry had their own OS, Nokia had their own OS called Symbian, and there were a couple of others. So you roughly had around 10 software, smartphone, or the pre-smartphone era, phone operating systems. Today you have two. Apple with iOS was first to market and is arguably best in class. And then everybody dropped their own base software to adopt Android, and now they're competing on price, hardware performance, hardware features, but not on the base software anymore. So customization happens through the hardware and differentiation and applications on top. And that's really where the car industry should be. You won't notice a difference between car A and car B, whether they run a different base software, as long as it works, doesn't fail, and allows you to update the software on the car, which, by the way, nobody today can do besides Tesla and maybe Rivian and a couple of the other new OEMs. But they started, or when they introduced their software platform, they at the time built a couple of vehicles. The largest car makers in the world, Toyota and Volkswagen, they build 10 million vehicles a year. That's a vehicle every couple of seconds. And there's a lot of legacy and carryover, both software and hardware, that actually works in those vehicles, where it's just very, very hard to do everything from scratch. Whereas the new car makers, they start exactly like this. They start with their software platform. They start with electric vehicles, with a so-called skateboard platform, where you really have the whole electrical powertrain on one so-called skateboard. But they come from a completely different starting point. They're not already at the point where they're making 10 million vehicles a year, or 1 million, which is as a smaller OEM, which is still a lot. Sure.
Can you hear me through Zoom? Can you hear me? I'm in the Zoom call. Can you hear me?
Yeah.
Yeah. I really like your response towards about how hardware-centric these autonomous companies are. So, for example, I used to work at a self-driving car company, and we still transfer LiDAR data using PCAP files. But my question to you is not about that. I'm curious, what led to the failure, if that's even to describe the word, of Faraday feature, if I may ask? I don't mean to be impertinent. I wouldn't say it.
So that's a longer answer. Let's have a coffee at some point.
Okay. Thank you.
Let's take one last question. I think there's somebody else actually coming in.
Yeah. You had the slide on centralization of architecture.
Mm-hmm.
Doesn't that increase security vulnerabilities? That's number one. And number two is that Microsoft and Amazon have made some moves in robot operating systems. How do you see the situation between closed versus open software?
Mm-hmm. So the first one was the centralization of software on computers leads to larger vulnerability from a security perspective. I would argue that it's easier to make one system safe than to make 100 computers in a car safe. So in any case, the vulnerability typically comes through the infotainment system, because that's what runs consumer electronic codes, for instance, in the Bluetooth stack, in the Wi-Fi stack for the USB connectors, which you just have to connect your consumer device. So you need to, usually through an onion principle, just shield those off. But that you have to do in any case. What was your second question?
Microsoft and Amazon versus open source.
With respect to, I'm not sure if I understand.
How do you see the adoption more of the open source software, or?
Oh, okay.
And given that these vendors move at a much faster product release cycle, right?
So in automotive, maybe the short answer is, for automotive infotainment, by far most OEMs are currently adopting Android Automotive to build the infotainment system stack. So that is the short answer. And is that open source? More or less, yes.
Right, thank you.
Well, thanks so much.
Yeah.